Welcome back to the lectures on the subRiemannian geometry of the Heisenberg group. We already saw that this structure is invariant under the group law, and therefore this geometric space is homogeneous in the sense that every point can be sent to any other point by an isometry, which in particular one can take to be one of these left translations. However, now today we will see that the space has also another kind of homogeneity. Very similarly as a Banach space admits a scalar dilation that dilates the distance exactly by a factor, these spaces have the same property. We are going to discuss the presence of dilations on the Heisenberg group. So for all scalar lambda say positive, we define the map. So delta lambda from R3 to R3, such that in coordinate x, y, z, a point is sent to a point where the first coordinate is dilated by lambda, the second one by lambda, and the third one by lambda square. Okay, so notice the square. Okay. Okay, now this map is going to be very important. So let's write it as a lemma, a proposition of what are properties of this map. For all lambda, so for all lambda and for all p and q in R3, what we have is, so first of all, we have that this map is a group morphism. P times Q is equal to delta lambda P delta lambda Q. So delta lambda is a group morphism. The second fact is actually is an isomorphism. It's invertible. So delta lambda is invertible, and the inverse is the dilation by 1 over lambda. So we have that delta lambda is invertible. And so an isomorphism. And these are just two algebraic properties. Maybe let's put a third one, that if you dilate by lambda, but before that you dilate by mu, this is the same thing of dilating by lambda times mu. Okay. Why I call it dilation? Okay, dilation is maybe a general term, and because what we are doing, we are stretching variables by some factors. But from the metric point of view, now we will see that this is really a dilation. This is the very important property that the Carnot-Karateodori distance between two dilated points is equal lambda times the distance of the 2 points. So this is said like delta lambda is a delta homotity. Okay, all these properties are very simple. Okay, so let's prove. So these are very simple exercises, but maybe I'll still do them. Okay, So 1. So delta lambda of p times q. Now let's remember, so this is you add the first variables, you add the second variables, and on the third variable you add the variables plus 1/2 p1 q2 minus q1 p2. Now we dilate, so we have lambda p1 plus p plus q1 comma lambda p2 plus q2 plus lambda square p3 plus q3 plus 1/2 p1 q2 minus q1 p2. Now you see, now multiply this lambda, okay? So you have lambda to each of the first coordinate, and now you see the third coordinate is multiplied by lambda square, and now you see this lambda square, think of multiplying with one lambda p1 and another lambda p2. Now really what you are going to see is that this is really the product between lambda p1, lambda p2, lambda p3 with lambda square p3, lambda q1, lambda q2, lambda square q3, which is exactly delta lambda p times delta lambda q. So lambda is an automorphism. Okay, so the fact that delta lambda composed delta 1 over lambda is the identity, this is obvious, right? So it's like you have in the third coordinate you're multiplying by lambda square and then dividing by lambda square. So and also, like, actually this is okay, a more general fact that if you have lambda mu, then what's happening to the third coordinate? So okay, let's say it's the lambda mu p1, lambda mu at the point p, p2, lambda square mu square p3, and of course this is just equal to lambda mu square. Okay, right, now let's go to the metric property. This is really the most important property, and maybe it's not immediately clear. However, let me argue why this is true in at least two ways. Okay, proof of DCC delta lambda p delta lambda q equal lambda DCC pq. Okay, so so first method. Now we see what we understood. So delta lambda is a map that is smooth, and I can consider the push forward of the vector fields. Okay, so if I push forward the vector field x, so x is a left invariant vector field. So if I push forward by a Lie group isomorphism, I'm for sure getting another left invariant vector field. But see, since you know what is the first component of x, which is 1, and you know how lambda behaves on the first vectors, then it's clear that this is going to be, or at least in the two horizontal vector fields, then this is going to be equal to lambda x. Likewise, okay, so let's say that these are leave as exercise. So, but once you notice this, then you understand that if you have a curve that is horizontal, then the dilated curve is also horizontal. Because the push forward of horizontal vector fields are still horizontal vector fields. And moreover, what is the length? The length is of these vector fields is exactly stretched by lambda. So this map stretches length by lambda. Infimizing the distance give you the condition that we wanted, okay? And the length of delta lambda composed gamma is equal lambda length of gamma. And this equation here is really an immediate consequence of this, okay? So we have this, okay. Okay, this was the first method. Second method. So let's use the fact that that we are in a homogeneous space, so we can left translate. So use that delta lambda is a group morphism, and that DCC is left invariant. In the sense, it's invariant by left translations. So what we have? We have that the CC distance between P and Q. Let's put lambda. Delta lambda P delta lambda Q. This is equal DCC. Let's multiply by the identity as now multiplied by delta lambda P inverse delta lambda Q. Okay, here I use the left invariance. Now let's use that that delta now is a group morphism here, and we have the DCC 1. This becomes delta lambda P minus 1 Q. Okay, so now this means that of course I can also do the same thing without the delta, right? And then what I'm left to prove is that if this is equal to DCC 1 P minus 1 Q, so which means that the equation that we have to prove here, in this equation, we can assume that one of the 2 points is the identity. Okay, remember the identity in the group is the origin is 0, 0, 0. Okay, I denote it by 1, but 1 in the sense of the element, the group identity. Okay, so therefore it's enough to show that DCC1P is equal lambda of this one is DCC1 delta lambda P. Okay, now of course one could also take a geodesic from 1 to P, which are leaves of circles, and see what happens when you multiply by lambda, right? And then you will see that this is still another geodesic, and you will calculate the length. Now let's make it even simpler. Now, you see, when we have to infimize the distance between 1 and P, right? We are taking, if P is of the form x, y, z, we are considering all points, all curves that go from 0 to x, y, that encloses area at z. Okay, so D1P or 1 x, y, z is equal to the infimum of the length of curves from 0, 0 to x, y, enclosing area Z. Okay, now apply delta lambda to a planar curve. Now, what happens? So first of all, the length. So since delta lambda restricted to R2, this is just the multiplication by lambda. Then lambda identity, right? Then the length of planar curves is stretched by exactly lambda. However, when you stretch, when you consider the map lambda times the identity, then the area of a planar curve, the area is stretched by lambda squared, by the Jacobian determinant of this matrix. Okay, so this is just lambda 0 0 lambda, and area is stretched by lambda squared. But this is exactly what the map delta lambda is doing. Is stretching, is sending the coordinate z to the coordinate lambda z. So in other words, delta lambda preserves the lift of curves and stretches the distance, the length by lambda. So delta lambda preserves horizontal curves and stretches length by lambda of either horizontal curves or of the three-dimensional curves. Okay, so and this proves the property for the metric. So the presence of a dilation gives us the homogeneity of the subRiemannian Heisenberg group. So homogeneity of the subRiemannian Heisenberg group So the Heisenberg group, as I said, is homogeneous in two ways. So first of all, there are the left translations that are isometries with respect to this subRiemannian distance. But then there is also this dilation that exactly dilates the distance by the factor lambda dcc q for all lambda greater than 0. Okay, let's rephrase this in terms of metric balls. So in other words, so let's define the metric open ball to be the points in space such that the CC distance from the center P is less strictly less, so it's an open set less than R. Okay, so this is called metric open ball of center P and radius R. Okay, so the presence of dilations and translation tells us a few things. So first of all, if I translate the ball at the origin of radius R, then I exactly obtain the ball centered at the point G with radius R. Second, if I dilate the ball center at the origin, radius 1, I exactly obtain the ball of radius lambda at the origin. So if I put these two things together, I have a formula for the arbitrary ball centered at P and radius R. To obtain it, I should just translate from on the left the dilated ball by R of the CC ball centered at the origin radius 1. So this in particular tells me that if we know the ball, the unit ball at the origin, then we actually know every other ball. This formula is not only interesting set-wise, really to say that we can calculate the arbitrary ball given the unit ball, but it's important that that it tells us how the arbitrary R ball grows according to these maps. Namely, if we know how these maps change measures, then we will know, given the volume of the unit ball, what is the volume of any other ball. So what I claim is the following, that so let's fix the volume, the usual three-dimensional Lebesgue measure in R3. So let vol be the 3D Lebesgue measure, Lebesgue volume in R3. Then the Heisenberg Carnot-Teodori or subRiemannian distance satisfies so the volume of an arbitrary ball centered at P with radius R is equal to R to the 4 volume of the ball at the origin, the unit ball. Okay, so before proving it, let's try to understand why this 4 is here. So it's really a strange phenomenon, because now we are in R3, where the Euclidean balls have volumes that grow as the radius to the 3rd power. But here there is no 3, it's 4. And why is this? This is because of the dilations, which are inhomogeneous. Remember? So we observe that if you have a point x, y, z in the unit ball, then if you dilate Rx, Ry, R squared z, this is in the ball of radius R. Now this dilation map, right, is a map that as a matrix is diagonal, and the determinant of this map, sorry, this is a square. So the determinant of this map is R to the 4. This map stretches volumes by R to the 4. Just vol by R to the 4. That's why we're going to have this proposition. Okay, let's prove it. Okay, so proof. So as we said, the ball is the left translation of the dilation of the ball of radius 1, the unit ball, center at the origin. Okay, In all of this, remember that the unit, the origin of the group is the point 0, 0, 0. But it's not very important in this calculation. So in other words, this is the left translation of the dilation of the unit ball. Now, let's consider the Jacobian determinant of these two matrices, of these two maps. What is the Jacobian determinant of LP and of the R? Okay, so the differential of the left translation we already calculated. We calculated to check that the horizontal vector fields were left invariant, I mean the basis x and y, and we saw that it was a matrix of this form 1, 1, 1, and what was important was here there was 0. Okay, now here there was minus y over 2, and here there was x over 2. Okay, now it's not really important to remember what it is, but we had some things here. Okay, actually no, 0 there, something here, something here. Okay, so this was a matrix, this form, and the determinant is equal to 1, right? 1, because here we have 0. So determinant is 1. Now instead the determinant of the left of the dilation, okay, again the dilation is linear. Sorry, so that's is R. Let me write R here. R square, and we have the determinant is equal to R to the 4. Okay, so we have that the volume of BPR is equal to R to the 4th volume of the ball centered at the origin, radius 1. Okay. If you like the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel clicking below. Bye.